Hello, my name is Jan Haak, and I'm an AWS Solutions Architect. Thank you for joining me in this session. So, why are you here? And who is this session for? Firstly, I designed this presentation for data scientists, machine learning engineers, and ML enthusiasts who are facing daily challenges around building a proper machine learning pipeline. The second type of audience for my session are builders and developers who have just started picking up skills and knowledge around machine and deep learning. At Amazon, we've been making huge investments in ML for more than 20 years. It's important to remember that many of the capabilities customers experience with Amazon are driven by machine learning. Our recommendations engine is driven by ML. The paths that optimize robotic picking routes in our fulfillment centers are driven by ML, and our supply chain, forecasting, and capacity planning are informed by ML algorithms. Our drone initiatives, Prime Air, and the computer vision technology in our new retail experience, Amazon Go, are driven by deep learning. We have thousands of engineers at Amazon committed to machine learning and deep learning, and it's a big part of our heritage. Across every industry, motivated, technically skilled companies are starting to meaningfully use ML in their businesses too. And more are choosing AWS as the place to do it than anywhere else. Today, I'm going to be talking about Amazon SageMaker. Amazon SageMaker is a fully managed platform that enables developers and data scientists to quickly and easily build, train, and deploy machine learning models at any scale. SageMaker removes all the barriers that typically slow down developers who want to use machine learning. Machine learning often feels a lot harder than it should be to most developers because the process to build and train models and then deploy them into production is too complicated and too slow. First, you need to collect and prepare your training data to discover which elements of your data set are important. Then, you need to select which algorithm and framework you'll use. After deciding on your approach, you need to tell the model how to make predictions by training, which requires a lot of compute. Then, you need to tune the model so it delivers the best possible predictions, which is often a tedious and manual effort. After you've developed a fully trained model, you need to integrate the model with your application and deploy this application on infrastructure that will scale. All of this takes a lot of specialized expertise, access to large amounts of compute and storage, and a lot of time to experiment and optimize every part of the process. In the end, it's not a surprise that the whole thing feels out of reach for most developers. Amazon SageMaker removes the complexity that holds back developer success with each of these steps. SageMaker includes modules that can be used together or independently to build, train, and deploy your machine learning models. There are a few terms that we'll be talking about today. I just want to quickly summarize them. Data science. It's what people do. It's a concept to unify statistics, data analysis, machine learning, and their related methods. And then sitting inside that, we've got AI. It's a marketing term that covers a broad range of technology. And then inside that, machine learning. It's a concept, again, not one that is particularly new, that uses statistical and mathematical concepts to give computers the ability to learn. Finally, inside the layer cake, we arrive at deep learning, a flavor of machine learning that uses mathematical structures inspired by the structure and function of a human brain that in areas like image processing, voice recognition, bioinformatics, and translation are producing results comparable and in some cases superior to human expert levels. So AI was founded as an academic discipline in 1956. And in the years since has experienced several waves of optimism, followed by disappointment and the loss of funding, known as the AI winter, followed by new approaches, success, And more recently, there's a lot of hype around AI. There are three main reasons why we see a resurgence in machine learning now. Firstly, vast amounts of data are required to train. Now, that's available and easy to store. Secondly, algorithms have improved and are much better able to scale out over farms of compute. And thirdly, training is extremely computationally hungry. More powerful hardware, GPUs like NVIDIA's Tesla V100 GPUs, are readily available, running on AWS as P3 instances, for example. And cloud is here. You can pay as you go. Machine learning is no longer just in the hands of the few organizations that can afford supercomputers. So what does this mean to you? As you can see, the analysts understand that the ML revolution is here. So our goal here at AWS is to put machine learning in the hands of every developer and data scientist. One of the important things to realize about these new flavors of AI that now are available is that you can solve problems that previously required human levels of attention. If you look at this image of a bunch of apples, it's easy to imagine that differentiating between a green and a red apple or an orange would be pretty easy to write in code. But what about when it came to telling if a piece of fruit was healthy or not, or if there was a particular type of fungus growing on it? This is where deep learning starts to become really interesting, because you can solve problems that previously you couldn't without humans. So here are a couple more examples. Firstly, medical imaging, and there's been a lot of success detecting things like diabetes simply from retina scans. From an industrial perspective, factories and processing plants tend to have thousands or even tens of thousands of sensors. Sometimes it's hard to make sense of all that data and predict when things are going to fail. Deep learning is really good at performing feature extraction. And in this example, it would be looking at those tens of thousands of sensors and then actually working out which ones are and are not significant in terms of having an impact on the particular problem you're looking at. Feature extraction is usually a pretty human-intensive activity. And the fact that machine learning can do a lot of the work for you saves a huge amount of time. You can build a recommendation engine, like if you bought product X, then recommending product Y. And a good example of that would be if you bought nappies or diapers, then it might end up recommending baby formula. And it's also really good at fraud detection. So think about financial transactions, tax accounting software, and we have a lot of customers building that kind of intelligence into their applications today. So a successful machine learning project has these 4 components built properly in a pipeline. Firstly, you need to get a hold of all the data necessary to build a model. And usually data in an organization is spread everywhere. So there needs to be a process to ingest, transform, and store all the data in a secure, scalable, and cost-efficient manner. In AWS, that probably means you want to put the data into S3. Then, data scientists and ML engineers start building the machine learning or deep learning models. This is mainly around massaging the data, some feature engineering, selecting algorithms, etc. After they have a pretty strong hypothesis around how this model needs to be trained, they start training. In some cases, clusters or high-performance machines with lots of GPUs are needed here. Then, when the model is built and tested and everyone is happy with the predictions, it's time to put it into production and integrate it with applications and processes. But what about when the model sees data from a new scenario that it doesn't understand, that it hasn't been trained on? This is where you need to start thinking about your machine learning pipelines as a cycle. Not just collecting data once, but as a continual process. Think of a driverless vehicle that has only been trained with vision of a road without ever seeing one that has snow covering it. It's pretty likely that the driverless vehicle algorithm is going to have some new problems when it hasn't seen that kind of situation before. So then you capture more data from production and you repeat this process to get a more accurate prediction or better inference. And these 4 steps may sound trivial and common sense to you, but I've seen too many failed projects and experiments where either the data part was not properly planned or the deploy part was not very well thought out, and it became a never-ending project where the return on investment didn't necessarily justify the efforts. So let's take a look at this process and look at the steps in detail. Let's start with the data. First thing that comes to mind is that for training a deep learning model, I need tens or hundreds of thousands of example images. Wrong. Let me tell you a little bit about transfer learning. Transfer learning is a method where you take a deep learning model, which is already trained on a huge image data set, and retrain it on specific objects where you have limited number of images in those categories. The way it works is that you get a neural network which is already trained on a big image data set, like ImageNet, which contains 14 million photos of pretty much everything. And this model is capable of recognizing shapes and edges and depths and color saturations and that sort of thing. In simple terms, this model is capable of recognizing an apple, but not necessarily different types of apples. So then you change the last layers of the neural network and train it on a few hundred images of apples. This process is called transfer learning. So you can use a pre-trained model and retrain it on a few hundred images to be much more specific about its output. So for other places to get more data, there are a few public data sets out there with different characteristics. For example, ImageNet, which was created by a team in Stanford and Princeton universities, contains 14 million labeled photos. Another good small data set is Caltech 256. This is a data set of 30,000 images of 256 different objects created by California Institute of Technology. Okay, now we have some idea around what data set to use. Let's get started building our model and have a look at the data set. The de facto standard way of working with ML data sets and building models is to use Jupyter notebooks. If you have some experience with machine learning and data science, you're probably already quite familiar with Jupyter notebooks. But for those of you new to this, Jupyter Notebook is a web app that allows you to create documents that can have live code, visualizations, and narrative text. And again, if you have some experience with them, you'll know how painful the process of building notebooks, installing different kernels, and then software, packages and libraries, and drivers can become. And then when you have it all configured, every time you need to SSH into the server, it can be confusing. This is certainly very unproductive, especially if there is a sizable team of data scientists working on the same project. For training data, exploration, and pre-processing, SageMaker provides fully managed notebook instances running Jupyter notebooks that include example code for common model training and hosting exercises. These notebook instances are preloaded with Anaconda packages and popular deep learning libraries like TensorFlow, Apache and Apache MXNet. So let me show you how. So here is SageMaker in the AWS console. Go on and hit Create Notebook Instance. And you can run the notebook in your VPC for access to custom resources. And in most cases, it's going to be fine to run it on a cheap T2 instance. Give it a name, hit Create, and you should be good to go. And as soon as it's in service, you can hit Open. And there you go, you've got your Jupyter notebook. Now that we have a notebook running, I should make some decisions around how to build my model, which basically means what algorithms to use, what frameworks to use. For example, TensorFlow, MXNet or Caffe. Amazon SageMaker installs high-performance, scalable machine learning algorithms optimized for speed, scale, and accuracy to run on extremely large training data sets. Based on the type of learning that you're undertaking, you can choose from supervised algorithms such as linear or logistic regression or classification, as well as unsupervised learning, such as with k-means clustering. The good news is that whatever method I want to use, I can do it on SageMaker. SageMaker was created with openness and flexibility in mind. It allows data scientists and machine learning engineers to develop models however they are comfortable, either bringing their own models or using one of the built-in SageMaker algorithms, or even using Apache Spark. So now we have the data, we selected the algorithm, we're going to choose one which is MXNet based, and most of the algorithms that come with SageMaker are like that. If I want to run this training on my laptop, it will probably take around a couple of weeks to finish. So maybe I could go and find a really big EC2 instance, and that would make it a lot faster. Maybe I could find an instance with a GPU. For a lot of types of training, that's even faster. And what happens if I decide to split the work up and run it on multiple instances in parallel? Well, that would make it faster again. But building a training cluster, even on AWS, is pretty time-consuming and requires decent knowledge of AWS services, automation, and in-depth knowledge of your deep learning framework's distributed training implementation. So what I'm going to do is use SageMaker as a training platform, which has everything ready for me to go. All I need is to provide a few bits of configuration. So let me show you. So we're back in the Jupyter Notebook, and you can click on a sample notebook. So go into the SageMaker Python SDK folder, and the example we'll use here is the k-means clustering. And here you can walk through an example of classifying handwritten digits using the MNIST dataset. So throw in a bucket name of an S3 bucket that you have permissions to access. You can create your own. It needs to be within the same region that SageMaker is running. And then hit the run button and you're off. And here are the parameters that go into the API call that goes to SageMaker managed k-means clustering algorithm. So you can configure how many instances you use in parallel to train, how many epochs of training to go through. And this example uses a pretty small data set, but Amazon's algorithms scale really well, even with multi-terabyte data sets. Okay, so we have a model trained and saved to S3. Now it's time to deploy it to production and run some tests. In the old world, this means a lot of work. Setting up auto-scaling groups on EC2 or on containers, load balancing, firewalls, CI/CD pipelines, as well as securing the API endpoints and worrying about encryption in transit and at rest. And there's a lot more to sort of think about here. And this is just on a cloud environment. Imagine if I wanted to build this on premises, I would probably need a few months and tens of thousands of dollars in advance, which wouldn't necessarily be a great idea for a proof of concept. So Amazon SageMaker has a great deploy feature where with a few clicks, you can deploy your model into production and set up A/B testing of different models in a highly available, infinitely scalable and secure fashion. After training, SageMaker provides the model artifacts and scoring images to you for deployment to EC2 or anywhere else. When you're ready to deploy your model, you can launch into a secure and elastically scalable environment with just one-click deployment from the console. SageMaker handles all of the compute infrastructure on your behalf with built-in CloudWatch monitoring and logging to perform health checks and apply security patches and other sorts of routine maintenance, as well as ensuring updates to the supported deep learning frameworks are applied as they become available. So let me show you how. So here, in these 2 lines of code, is a pretty incredible thing that is happening. Firstly, you're deploying the model that you've built in previous steps onto an endpoint, defining the kind of instance that you want to run inference on, as well as how many initial instances you want to take the load. In this example, it's just 1, but if you were to set that to 3, it would automatically run those instances across multiple availability zones and give you a highly available architecture. The next line is simply calling the endpoint that was created and putting some data through it to get a result. And here we can see the result is that we've classified different clusters of handwriting that the algorithm has deemed are similar in some kind of manner. And as it turns out, this kind of algorithm may not actually be the best way to recognize handwriting, but it's a pretty useful exercise to go through, and it will only take 10 minutes or so for you to do. But I guess the real key thing to think about here is, instead of calling those endpoints from inside a Jupyter notebook like we have in this example, think about calling the endpoint from your app. So is your app taking in a photo or bringing in visual information or audio and then trying to recognize something within that? This is the point that you'll be able to call in order to run that inference. So just to recap, I used a SageMaker notebook instance in the cloud with no hassles like installing drivers and kernels. And then I selected the distributed built-in k-means clustering algorithm, which comes with SageMaker, to speed up my build time. And then with a few lines of config, I submitted a training job using a huge amount of compute in which I only paid for usage by the hour. Hyperparameter optimization is another feature of SageMaker, which I'll talk about in a minute. And then I deployed my model into production, ready to receive thousands of requests per minute. This is highly scalable, available, and secure. So what can I do to make it even better? You guessed right, I could do much better with more and better data. The general rule of thumb here is that the algorithms are pretty commoditized, and the real competitive differentiation is in your data set. And generally, if you had to choose between a better algorithm or more data, you're probably going to get a better result simply by adding more data. When the training is over, the data scientists spend a lot of time on fine-tuning their models to get better accuracies and to run faster. This fine-tuning is called hyperparameter optimization, or HPO. HPO is usually a painful and long process that requires lots of trial and error. In SageMaker, we have built a feature that does HPO automatically by spinning up multiple training jobs in parallel and running hundreds of different combinations of algorithm parameters until achieving a certain accuracy or hitting the set time constraint. As most of these hyperparameters are generally regarded as a black art, AWS can make fine-tuning a much more scientifically rigorous exercise, and you will end up with a better model as a result. Or what about when I use multiple data sets or multiple sets of hyperparameters? I want to know which ones are actually giving me better results in real life. So this is where I can use the A/B feature testing of SageMaker deployments quite easily. This means I can deploy 2 or even more different models at the same time. For example, one model that I know works, but it's a bit old, and another model that I think is going to be great, but I'm not entirely sure how it's going to go, and I don't want to throw the baby out with the bathwater. So this lets me test models against each other and make sure that I'm actually releasing a new model that is better than the previous one. So today we've gone through in some detail the process of collecting data, building a machine learning model, training and refining that model, and then deploying it to an endpoint so that inference can be run. And remember, you don't have to use all of the pieces of SageMaker. For instance, if you wanted to deploy the model onto a mobile device or onto an IoT device, then remember that the outputs of SageMaker aren't in any proprietary sort of formats. They're all the open ones that you already would be used to working with. And as a specific example of that, our IoT edge service, Greengrass, now supports the deployments of models instead of to a web-based endpoint that we demonstrated, managed by SageMaker. You can deploy the model onto an IoT device. And this is useful when your ML inference can't rely on an internet connection, or you're in a remote location and you simply don't have the bandwidth to send the data to the cloud. Deep learning and SageMaker give you a new set of tools to solve problems that previously would probably require human levels of attention, and it allows you to solve problems based on all new kinds of input, like video, like audio, that previously were inaccessible to traditional machine learning techniques. To gain more confidence and hands-on experience with AWS, access the digital training built by AWS experts. Attend our instructor-led classes by qualified AWS instructors and learn how to design, deploy, and operate highly available, cost-effective, and secure applications on AWS. Validate your technical expertise with AWS and use practice exams to help you prepare for AWS certification. We also have a wide partner ecosystem to help you focus on your success and take full advantage of all the business benefits that AWS has to offer. Learn more about how APN partners can help you and find the right APN partner for your needs by visiting the AWS APN booth at our showcase. Thank you very much for your time.